So let us discuss a question based on this radius. So here, what is the radius of second orbit of helium plus ion here? So here what is the formula? Rn equals to 0.529 n square by z square, n square by z angstroms, right? Okay. So what is the orbital number, orbit number here I mentioned? Second, R2 of helium plus I am asking. So 0.529, what is the n square? 2 square 4. Okay, and the next is Z. What is the atomic number of helium ion? So it will be 2. Atomic number is 2. Z value is 2. So that's what. Yes. Finally we got. So how much? 0.529 into 2 angstroms. Okay. So now this sometimes what they will be giving is, you can simplify this, or they will be giving this value as A0. Okay. This is the A0 value. So we should write it as 2 A0 angstroms. So this will be the value of like A0, R0, there will be the, see, radius of first orbit of hydrogen is R0. Then what is the relation between the radius of first orbit of hydrogen to the radius of second orbit of helium plus ion? So like this they will be asking. So in that case you should answer in this manner. Okay. So here you just multiply this number, you will be getting the final answer. I hope it is clear without any confusion, right? So the next, let us have one more question here. So the difference in the radius between the fourth and third Bohr orbit of helium plus. So I should write difference. Difference means the fourth, R4 minus R3 of what? Helium or helium plus. Okay. So atomic number of helium plus will be 2. Z value is 2 and n values are mentioned here. So what I can say, so what is the radius formula? 0.529. 0.529. This number is common in both of these cases now. So instead of writing 0.529, let us take 0.53. So for our simplification purpose, okay, 0.53 into, okay, 0.529 n square by z square. Now z also same here. So I am taking this as common z. So what is the z value? 2. Okay. Then next, what is the n square here? N4. N4. I mean like fourth orbit na, n4 square minus n3 square. Okay. So what is the n4, like fourth orbit they are saying na. So you can directly take it as 0.53 by 2 into 4 square 16, 4 square 16 minus 3 square 9 you can take. So finally we will be having an answer like this. So 0.53 into 7 by 2. So by simplifying this we will be having, see, this data, see, whatever the data I have mentioned here, the formula which we have used is Rn equals to 0.53 n square by z. This is in angstroms, right? So we know 1 angstrom is 10 power minus 10 meters, right? So I can multiply, because all the options are in meters. So they mentioned it should be in the meters. So you can multiply this with angstrom replacing with 10 power minus 10 meters. Therefore it will be also 10 power minus 10. So here also it will be 10 power minus 10 meters. Okay. By simplifying this, so we will be having answer like 1.85 into 10 power minus 10 meters. So which is option C is correct for this particular question. I hope it is clear, there is no confusion. Then next, here we have the radius of first Bohr orbit of hydrogen atom is same as that of the hydrogen like species X, and what is the N and X respectively are. So they are saying that radius of first Bohr orbit. What is the radius of first Bohr orbit of hydrogen atom? This is 0.53 into n square by z we are writing. Okay. So this 0.53 I am writing as it is. Okay. What is the n value they mentioned? First 1. So what is the hydrogen atom atomic number? That is also 1. So this is the value, 0.53 is the value for radius of first Bohr orbit of hydrogen. So this value should be same for which of this? Which option will be having the same value? It means this n square by z ratio should be same. N square by z ratio is same, like equals to 1 means in which case it will be valid. So here see, n value is 2. In the option A, n value is 2. N value is 2. N value is 2 means 2 square 4 by atomic number of lithium is, lithium plus is 3. 3 means 4 by 3. This is not equals to 1. Similarly, if we do this, so it is 3 square 9 by 3. That is also not equals to 1. So, but here if we take third option, see, or 2 of beryllium, Be plus 3. So what we can get? 0.53 into n square, n value is 2, square means 4 by beryllium, atomic number is 4. So 4 by 4, that will be 1. So this will be equals to the R1 of hydrogen. So which option is suitable? So third option is suitable answer for this. Then next, radius of third orbit of hydrogen atom is R. Okay, the radius of second orbit of helium ion is how much? Okay, so in terms of R. So will you give a try for this question? So take this question as a homework, hashtag question number 1 as a homework. So write answer, give this answer this question in the comment box. I will be waiting for your answer. Okay, so mention it as hashtag 1 and answer the question. So I hope you will definitely do this question. Then next, calculation of energy. Okay, so energy of an electron in which like the orbital in which this electron is revolving. So how can we calculate this? So we know total energy is sum of kinetic energy and potential energies, right? So this kinetic energy is given like this, kZe square by 2r, whereas potential energy is given as kZe square by r. Okay, so now by looking into these two things, these two things will be giving something like this. So now what is the relation between them? Total energy equals to this much, minus 1 by 2 kZe square by r. Okay, so it means can I write, see this is having, see this is half of this potential energy, right? So that is why half of this potential energy it is mentioned with the same negative symbols, but kinetic energy is having same like same magnitude but opposite sign, right? kZe square 2r. So that's why it is having opposite sign. So total energy equals to minus of Ke or 1 by 2 of potential energy. So what is the ratio here? We can say half 1 plus 1 minus 1 1 by 2. So in this format you can write, or you can also write like this, 2 is to minus 2 is to 1. So kinetic energy, potential energy, total energy, kinetic energy, potential energies are in these ratios. You can answer like this. I hope it is clear, no confusion. Then next, okay, so what are the values here? So by simplifying this kZe square by r, we will be getting, see here except z and r, see what is the r here? Radius. So again we have radius value, na radius, we got the final derivation, right? So by substituting here the constants and everything, so we will be remain with this. So we will be finally remains with this, minus 13.6 z square by n square. This is the formula in terms of electron volt per atom. Okay, and total energy in terms of joule per atom is this one, minus 2.176 into 10 power minus 18 z square by n square. Okay, then total energy in terms of erg, so you can take like this. Okay, I hope it is clear. So how can we relate electron volt and joule? So this is the relation, 1 electron volt is equals to 1.6 10 power minus 19 joules, 1 calorie equals to 4.18 joules. So based on this we have relation for calories also, minus 313.6 z square by n square kilocalorie per mole. Okay, so these are the relations which you need to remember. All these 5 formulas are important. Sometimes depending upon the question we have to use the formula, because they may give the different units. So according to the units of the particular question we need to answer. Okay, now here see, in this case energy of electron in the ground state for helium ion is minus x joules. Then what for the electron in N2 state of beryllium plus 3 is? So this is simple question now. So what they are saying, energy of electron in ground state E1 of what? Of helium plus, they are saying like this. So what is the basic formula we have? Energy of electron in nth state, okay, is given as, let us say in terms of whatever it is, see we can generalize that in these terms now, which is directly proportional to minus, like see here what we have. So minus is there now, everywhere it will be minus, so that's what I am taking minus. So they are asking in joules, whatever it is, so we can take this directly. What is the common thing here? Z square by n square now. So that's why I am taking z square by n square, like this we can take. Okay, so now energy of an electron in the ground state of for helium plus is minus x joules. Okay, so if it is the case, so I am taking, okay, I am removing this proportionality and writing it as minus k, and what is this z for helium plus? So that is 2, atomic number is 2, square 4 we can take, and n value is how much? Here it is 1. Okay, so this is what I have taken, n square, so here 1, right? Then next, okay, similarly E, then next what, then that of electron in N2, N2 of what? Beryllium, Be plus 3 is given. Okay, so now here what is the relation we will get? K again. So what is the Z value for beryllium? Atomic number is 4, square 16 we can get, and atomic number is 4, and n value is 2, 2 square is 4, okay, like this. So we can remove this 2, so this is 4 times, again 4 by 1, 4 by 1, everything is cancelled. So E1 of helium is how much? Energy of first state, ground state of helium is minus x. If this is minus x, here it is equals to 1, no? So for E2 of beryllium also becomes what? Minus x only, no? Because both are like ratio is equals to 1. It means E1 of helium plus, which is equals to minus x, which is also equals to E2 of Be 3 plus. So this is how you can do. So what is the suitable answer? Option number 2. Okay. So very simple questions are there. Okay. So now see, now we have formula. What is the basic formula we have seen there? So electron volt formula let us take. En equals to minus 13.6 Z square by N square electron volt per atom. This is a formula they have given. So now ground state, when n equals to 1, let us say this is hydrogen atom. So E1 of hydrogen atom, if I want to write, for hydrogen atom, what is the Z value? Atomic number will be 1. So 1 by 1. So what is the ground state energy? Minus 13.6 electron volt. Okay. Then next, if it is second, then it is second energy. I mean, this is a ground state. First, like ground state n equals to 1. So this is n equals to 2. I can say first excited state. What is this? This is a ground state. This is first excited state. For first excited state, what is the n value? It is 2. So n value is 2 means atomic number remains some, n is 2. So 2 square 4. So 13.6 by 4. So this will be minus 3.6 electron volt, 3.4 electron volt. So like this, see we are getting n equals to 3, n equals to 4 like this. If we go on, the values are like this. Okay. So from here to here, what we are observing? Energies are increasing. The lowest energy is in the ground state. So whenever electron lies in the ground state, the atom is more stable. Then the electron is lying in the higher energy state. Okay. So more like low energy, more stability. What I am saying, low energy, more stability. See, if this is the like energy E equals to 0 when an electron is very far from the nucleus. If it is infinitesimally, like if infinitely away from the nucleus, the electron is away from the nucleus. Okay. So then that case energy is 0. So in the remaining cases, when it is coming closer to the nucleus, so initially what it is saying, so electron is away from the nucleus, which is separated by with the infinite distance. But when we are moving them, when we are keeping them very closer, so the stability of that species is increasing by lowering the energies. Okay, this is one thing you should remember. Now the ground state is having this much, say first excited is having this much. As we going away, as we going as the n number is increasing, what happens to the energy values? Energies are increasing, but the energy gap, what happens to the energy gap? Energy gap is decreasing. See, for E2 minus E1, this E2 minus E1, what is the difference? Here we got 10.2 electron volt. What about E3 minus E2? We got 1.89, which means the energy gap is more in the first case, which is decreased, again decreased as we go above side, like top side, like upside. So what happens, the energy levels are becomes very close to each other like this, very close to each other. Okay, it means energy gap is decreases as we move up. Okay, so the energy, see the difference between the energy levels will be decreases as n values increases. This is what you need to remember. See, two things I am writing here. These are the statement based questions you can expect. So as n value increases, energy increases, and difference between the two energy levels, that is delta E, decreases. This is what the statement you should remember here. Okay. Then next thing is, see I told you electron, excitation of electron takes place from lower energy to higher energy. Let us say electron is in the ground state. So in order to excite to the next energy state, like first excited state, so how much energy is required? By absorbing 10.2 electron volt of energy, this electron can jump from ground state to first excited state. If we supply only 10 electron volt or 9 electron volt, which is not sufficient, right? Therefore excitation will not be taking place here, will not be possible. Only by absorbing 10.2 electron volt of energy it can jump. If energy supplied is lesser than that, the electron excitation won't takes place. Okay, I hope it is clear. Okay, now the absorbed, since it is absorbing the energy, so we can get absorption spectra. If an electron is falling from this higher energy state to lower energy state, energy is emitted, then we can see the emission spectra by absorbing the by analyzing the that emitted energies. I hope it is clear, right? So now what is the wavelength? Wavelength associated with absorption or emission of the photons. Okay, so how can we see? This is the Rydberg's equation. I can say 1 by lambda equals to RH z square 1 by n1 square minus 1 by n2 square. This is the equation. So always remember n2 higher energy state, then n1. Okay, this is the thing you need to remember. Okay, so this is known as Rydberg formula. I hope it is clear. Okay, if we want to find delta energy difference, so we can also use this relation. Okay, or we can directly use, if they give delta energies directly they give in terms of electron volts. So what is the E value for energy formula for in terms of electron volt? That is what? Minus 13.6 z square by n square we are writing now. So it means I can make a formula here, 13.6 into z square for a particular element, 1 by n1 square minus 1 by n2 square. So this is also we can use in terms of electron volt per atom, the energy difference. We can use this formula also. Depending upon the requirement, we can vary. We can use the different formulas. Again, when it comes to velocity, this is the formula we need to use. 2.18 into 10 power 6 z by n meter per second. Okay. For example, electron which is revolving in the second Bohr orbit of helium place, if they give like this. So what we can do? Velocity they are asking. So we can find velocity of second Bohr orbit, which is in the electron in the second Bohr orbit of helium place, is equals to 2.18 into 10 power 6 into, so what is the n value they mentioned? Second Bohr orbit. So n is 2. Okay. So for helium, what is the atomic number? Z is 2. So 2 by 2. So this is cancelled. So we will be remained with a value like this, 2.18 into 10 power 6 meter per second. This is the final value. Okay. Then next, here we have hydrogen spectra. See, this is for hydrogen atom. Let us say here there are different spectral lines possible for a particular atom here, for a particular hydrogen spectra. Let me tell you. Here again, see guys, this is one of the important things. See here, the number of spectral lines possible in this case. See, for example, an electron is at the at one. See, let us say one electron is lying at the higher energy state. So that electron can jump to lower energy state in different pathways, right? For example, electron is lying in the n equals to fourth state. So electron in this state. So now what happens? So this electron can, so from here it can directly jump to the ground state, or it can falls into the second energy state, or it can falls to the third energy, right? Or after reaching the second, it can again comes to down, or from third to 3, like this different possibilities are there now. So now when an electron is directly falling from nth level to the first state, ground state, the first energy state, n equals to 1 state, we should say all those lines are called as Lyman series. What I am saying, any higher energy state to first state, those lines, those spectral lines are called as Lyman series lines. They will be appear in the Lyman series, that is what UV region. So they will be appeared in UV region. Okay, if electron is falling from any nth level to the second energy level, that is what n equals to n equals to 2 level, we can say all those lines are considered to be Balmer series lines. So these are appeared in UV spectral region and these are appears in visible spectral region. And if electron is falling from any nth level to the third energy level, so that comes in the Paschen series line. So this is n equals to 3 third level. When electron is falling from any nth level to third energy state, we can say these lines can be Paschen series. So again, any level to fourth bracket, any level to fifth fund, any level to sixth Ampere. So like this we have to consider. Okay, so now see, now whenever we have n2 minus n1, n2 minus n1 is equals to 1, then we can say that line is alpha line. So for example, Lyman series, what is a H alpha line, H alpha line, H beta line, we can say. So H alpha line means, so alpha line means what is the difference we should get, n2 minus n1 should be 1. So it means electron should fall from second energy state to first energy state. We can say that respective line as H alpha line. Okay, if electron is falling from n equals to 3 to n equals to 1, so what is n2 minus n1, 3 minus 1, so this is what 2. So we should call it as H beta line, H gamma line, like that we should call. And last line from infinite to first level, we should say H infinite line. Okay, so now this last H infinite line and H infinite line and H alpha line are the limiting lines of that particular series. What are the limiting lines of Lyman series? One is H alpha, which is n2 to n1, the difference is 1, and what is the last one, n infinite to n1 will be considered to be the limiting lines of Lyman series. Okay, so now tell me, what is the alpha line of this Balmer series? So how can we say alpha line or first line of Balmer series? So first line or alpha line of Balmer series if they ask. So from any higher energy state to second energy level, right? So n2 should be 2. So they can come from any of the higher energy state. So n can be any state, but they should fall into the first energy level. Okay, so if it is falling from 3 to 2, so I can say this is Balmer series line. And see what is the difference, like 3 minus 2, this is 1, difference is 1. So if it is difference is 1, H alpha line or first line of this Balmer series, like this we should answer. I hope it is clear. So what is the, like I am asking a question now, what is the alpha line, what is the alpha line, or I can say H alpha line or first line in Paschen series. Paschen series first line is what? So Paschen series means what? N should be, so n1 should be 3. So from any energy level to this level, so any nth level to this level, if electron is falling, we can say Paschen series line is that line belongs to Paschen series. Now I am asking first line of Paschen series. It means from where it should fall, from 4th to 3, 4 to 3, therefore difference is 1. So okay, I can say first line. So if I ask you second line, so it should fall from where to where? So first line means 4 to 3, the difference is 1, so I can say first. So I am saying second line 5 to 3, that will be the second line, the difference should be 2. Okay, now I am asking you, what is the third line of Paschen series or gamma line of Paschen series? If I ask, what is your answer? So write in the comment box. Okay, so now what are the regions, spectral regions in which these lines are appears? UV visible, so for Lyman UV, Balmer visible, Paschen infrared, and other things also infrared, you can remember like this. Okay, so these are important here. So there is a question here, see, which are the following transitions in the spectrum of hydrogen falls in the visible region? So visible region is what? Second one now. So first one is Lyman, second one is Balmer. So option 2 is correct, right? Here you can see Balmer series appears in visible region. Okay, whereas Lyman appears in UV. Okay, and these two things are appears in where? IR, infrared. So this is one of the important topic. Okay, so now the third line of Balmer series corresponds to electronic transition between which Bohr's orbits of hydrogen. So third line means what? In Balmer series, so n1 must be 2, right? Okay, so if n2 is 3, so the difference is 1, so I can say first line. If N2 is 4, the difference between these two is 2, this is second line. N3 is 5, N2 is 5, so difference between them is 3, so this is our third line. So from where to where? 5 to 2, so this is the correct answer. So option 2 is the correct. I hope it is clear, there is no confusion. Okay, so now I will be asking you what is the shortest wavelength of helium in Balmer series. The shortest wavelength of helium in Balmer series is X. The longest wavelength in the Paschen series of lithium is. So very simple now. So use this formula and tell me the answer for this. 1 by lambda equals to RH Z square 1 by N1 square minus 1 by N2 square. Okay, so use this formula and try to answer this in the comment box. I will be waiting for your answer. Okay, then next, here what are the ground state energy differences, energy ratios. So how can I write the energy ratio for a particular species? Like this, if we give any atom, any ion is given, so what I can write? Minus 13.6 Z square by N square we have. So this thing is common now, so I am taking this as common, which is like this. Okay, so what I can say, so for ground state, so N value also constant, only this Z value is varying. For lithium, what is the N value, Z atomic number? 3, right? 3 square 9. Okay, then next, for helium, what is the Z value? Atomic number is 2, so 2 square 4. Then next, for hydrogen, atomic number is 1, 1 square 1, 9 4 1. So option C, very simple, right? Next, electron jumps from 4th to ground state of helium. Calculate amount of energy released. So very simple now. So what I told you, you can use this formula, 13.6 Z square 1 by N1 square minus 1 by N2 square. So this is a formula we can use. So energy difference we can get, because in terms of electron volt they are asking. So 13.6 for which element it is? Which element they are asking? Helium. So you can take hydrogen, helium atomic number 2. So 2 square 4 we can say 1 by, what is the energy? First energy level, lower energy one is second. So N1 is 2. So 2 square is 4 minus N2 is, see, from 4th. Higher energy state is 4. So 4 square is 16. So by simplifying this, you will be getting one of the options. So you can choose that. Okay, then next, the total number of spectral lines observed when electron returns to 6th shell until the second energy level. So here I have given a formula here. So you need to write this formula in your notes first. So this is one of the important formula which you need to highlight in your notes. So let me show you here. See here. See, the number of spectral lines possible spectral lines produced when electron jumps from nth state to first energy state. Any energy, higher energy state to ground state, you can use this formula. So instead of remembering this, just try to remember number of possible lines produced when electron is jumping from any state to another state. So N2 to N1 state, let us say. So that time we have to use this formula, 1 by 2 N2 minus N1 into N2 minus N1 plus 1. So that is what the formula we need to use. So let us practice here with this question once. So what is the formula I told you? Number of spectral lines, number of possible spectral lines, let us say. Okay, so what I told you, N2 minus N1, so half into N2 minus N1, so N2 minus N1 plus 1. So this is the formula we need to use. Okay, so half into N2, what is the value? N2 6, 6 minus 2, that is 4. Okay, and again 6 minus 2 plus 1, so 4 plus 1, 5. So here 2, so 10 lines will be obtained, 2 5s are 10, so 10. So this is how we need to answer this type of questions. So I will be explaining one more thing here. Okay, the total number of spectral lines observed when electron is falling. Okay, done, this is. Then next, this is also done, we already done with this. Calculate maximum number of spectral lines possible. See, for example, these are the energy state. This is 5, 4, 3, 2 first energy states. Electron is at the 5th excited state, I mean 5th energy level. Okay, 5th energy level. If I say 5th excited state, it should be the N value should be 6, but N value is mentioned as 5th. It means 4th excited state it is. Okay, so electron directly falls into first state this is the one spectral line possible, or it can falls into the second, or it can falls into the third, or it can falls into the fourth. This is one thing can be possible. Okay, now from 4 to 4 to 3 it is possible, and 3 to 2 it is possible, right, and 2 to 1 it is possible. Now just count number of spectral lines possible here. See, is there any other possible way? See, from directly 4 to 2 also it can come, right, and directly from 4 to 1 also it can come, right, and from 3 to 1 also it can come. So how many spectral lines possible here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 possible spectral lines are there. So like this also we can calculate actually, but it will be time consuming, right? So directly use a formula, half into n2 minus n1 into n2 minus n1 plus 1. So if you use this formula you can get. So see, what is the n1 value? So n2 is 5 and n1 is 1. So n2 minus 5 minus 1, that is 4 here I am writing. What is the n2 here? 5 again, n1 is 1. So 1 minus 1 0, 1 plus 1 0, minus 1 plus 1 0. So here I am writing again 2. So again 10 lines are obtained. So what is the answer for this? 10 lines. I hope it is clear, there is no confusion in this discussion, right? So then next we have limitations of this Bohr model. So what are the limitations? So this Bohr model, till now we have seen hydrogen, helium plus, beryllium plus 3, lithium plus 2, like this, right? So this is valid only for single electron species but not the multi-electron system. So it is failed to explain the multi-electron system. Okay, so multi-electron system fails for multi-electron system. Bohr model could not explain the interactions in the more complex atoms, right? Then next, it was unable to explain the fine spectrum of atom. Okay, now next it was failed to explain Zeeman effect, Stark effect. Okay, Zeeman effect means what? The spectral lines we have seen now, the splitting of the spectral lines, presence of magnetic field is there. So that was not explained in the Bohr model. Again, Stark effect. What are the spectral lines we have studied? The splitting of spectral lines takes place in presence of electric field. That was also not explained in Bohr model. Then next, it contradicts Heisenberg's uncertainty principle and suggests, so this is what suggests precise orbits violating quantum mechanics. Okay, so this is one contradiction. And the next, ignores wave particle duality. Like this is what here de Broglie's wave equation, right? So these are the two contradictions which was not given in the Bohr model. Okay, so this is about the Bohr model, like postulates and formulas and the derivations, and the next limitations also. Okay, I hope this session will be highly helpful. If you really like the content, just click on the like button and also share with your friends. Thank you for watching.